So this is an overview of titrations and two sample problems. First of all, a titration is when you take an acid and add it to a base, and you get as products a cation and an anion, which is also known as a salt, and some water. When equal moles of acid and base have been added, you are at what's called the equivalence point of the titration. Equivalence point means there's equal moles of acid and equal moles of base. Equal moles does not necessarily mean you're at a particular pH, as we'll see in the sample problems. There are four different types of titrations that we'll look at, and what occurs to them, and whether they're acidic, basic, or neutral at their equivalence point. First of all, if it is a strong acid plus a strong base titration, you'll produce a salt and water, and the salt will be a combination of a positive cation from a strong base and a negative anion from a strong acid, which will effectively be neutral because they will not act acidic or basic. And so it will be neutral, or it will have a pH of 7 at the equivalence point. The second type of titration is a strong acid and a weak base. When a strong acid is added to a weak base, you will produce a base that has gained a proton that forms a conjugate acid, and therefore at the equivalence point the solution will be slightly acidic. The third type is if you have a weak acid and a strong base. When you combine these two, you'll form the conjugate base of the weak acid, because these two, of course, will be canceling each other out because there's equal moles. This conjugate base of the weak acid is slightly basic, and therefore at the equivalence point the solution will be basic. The last type is if there's a weak acid and a weak base. The pH of the solution at the equivalence point here depends. It depends on which of the weak acid or the weak base is stronger. And you need to look at the Ka and the Kb to determine this. Lastly, let's look at a pH versus volume of titrant graph and take a look at how it changes as the titrant is added. This is an example of a weak acid versus a strong base, where a strong base is the titrant being added to a weak acid. Three things to notice on this graph. First of all, notice where the graph starts. It starts at a pH of approximately 4. Notice that if it were a strong acid, it would start at a lower pH, and you can identify a pH titration graph and the type of acid or base it is, strong or weak, just by looking at the starting pH. Secondly, take a look at the equivalence point. The equivalence point always takes place in the middle of the steepest part of the graph. If this were the steepest part of the graph, the equivalence point would be right here in the middle, and therefore we'd have an equivalence point happening somewhere around a pH of 9 or a little bit above or below that. Notice that the pH at the equivalence point is slightly basic. That's because the weak acid has been completely consumed and it's formed its conjugate base. Thirdly, the thing to look at is the point that is halfway to the equivalence point. The point halfway to the equivalence point would be from the beginning to the equivalence point cut in half, right about here. This area has the lowest slope and is the area of most buffering. And it's the area of most buffering because you will have some of the acid still remaining in the solution and also a good amount of its conjugate base. And remember, a weak acid conjugate base pair makes a buffer solution, and that's why the pH does not change very readily during this point halfway to the equivalence point. If you look at the calculation of the pH of this buffer solution, you could use the Henry-Hasselbalch equation, where the pH is equal to the pKa plus the log of the base divided by the acid. if the concentration or amounts of base and acid are equal, this log goes to 0, and therefore the pH is equal to the pKa. And so if you're given a pH versus titrant graph, and you can find the area of most buffering and therefore halfway to the equivalence point, you could follow this over, and it would tell you the pKa of the acid. In this case, the pKa of the acid is about 5. There have been multiple choice questions about this in the past, and they've asked you which acid it is for this particular titration, and they give you a list of pKa's. All you simply need to do is find the halfway to the equivalence point, and then look over to the vertical axis of the graph and determine which one is closest, which pKa is closest to the pH at that particular point. Now let's work 2 sample problems of weak and strong acid-base titrations. These are in your sample problem handout, and please take it out at this time along with a calculator. Calculate the pH at the equivalence point when 40 milliliters of 0.025 benzoic acid is treated with 0.05 molar NaOH, and it tells you to look up the Ka. Well, first of all, it's nice to know the equation to benzoic acid, but in case you don't know it, that's okay. You know that weak acids always have a hydrogen atom, and then you can just make up whatever the anion is, and I'll just call it H-benzoic, because I know I've got a hydrogen atom, and I've got the hydrogen cation, and I've got a benzoate anion, whatever it is. And it's titrated with NaOH. So write down NaOH. This is always the first step of a titration, is write the balanced chemical equation, giving a proton away. When this reacts, you're going to get some sodium benzoate, or some sodium and the benzoate ion. We know that sodium's not going to do anything in the solution, so I'm going to write down benzoate, and I'm going to put a minus sign here because it's going to dissociate because it's a soluble salt, and some Na plus right here, and we'll also form some water. Of course, water's not going to have any effect on the system. The sodium ion's not going to have any effect on the system as well, because it's what's left over after a strong base has used up its OH. And the benzoate, of course, is what's left over after the acid has released its proton. And so this is called a conjugate base. And a conjugate base of a weak acid is going to act slightly basic. Now it tells us that we're going to be at the equivalence point. And at the equivalence point, we know that we're going to have equal moles of acid and equal moles of base. So if we find out the moles of one of the things, we'll know the moles of the other. It tells us in the question that we have 40 milliliters of 0.025 molar benzoic acid. And so using the molarity triangle, molarity is equal to moles divided by liters, we could find the number of moles of benzoic acid in the solution. Moles are equal to molarity times liters. The molarity is 0.025 molar. The liters are 0.04 liters, whoops, L, and this is going to equal 0.001 moles. 0.001 moles. That's how many moles of acid and base there are at the equivalence point. Both are equal to each other. So at the equivalence point, I could write an ice table for this, but I know at the end I'm going to end up with 0 of this and 0 of this, and all of it's going to be converted to these products over here. And we've already determined that these 2 products will have no effect on the pH, and so in the end I'll end up with 0.001 moles of the benzoate ion. I know the benzoate ion is going to act basic in solution, and so I'm going to write an equation of benzoate ion reacting with water, acting basic, and then ice table that to find out what the concentration of the benzoate ion is. Now, to do this, to figure out what the OH minus concentration is eventually as benzoate acts basic, I'm going to have to look up the Ka or the Kb of benzoic acid. And if I look in the back of the book, I'm not going to find benzoate ion underneath a table of Kb's. What I am going to find, though, is the Ka of benzoic acid. And at this time, I also find out that the equation for benzoic acid is HC7H5O2, which hasn't really been significant, and it's still not significant now. It's just interesting to know the formula. The Ka for this is 6.3 times 10 to the negative 5th, and this will help me answer the question of how basic the solution is. So I can write my equation now saying C7H5O2 minus the benzoate ion reacts with water, and it's going to act basic. Remember, it's a conjugate base, so it's a weak base. And I'll make some HC7H5O2 plus some OH minus. My goal, of course, is to find out what is the concentration after I ice table it of this OH minus, because that'll help me find the pOH and therefore the pH of the solution at the equivalence point. I can write an ice table for this, and when I do that, what I need to know is the concentration of C7H5O2 minus. To be able to do that, of course, I not only need to know the moles, of which there are 0.001 moles at the equivalence point, but I need to divide that by my total number of liters at this time. This is a tricky thing to find. It's not so hard because it only involves the molarity triangle. Molarity equals moles divided by liters. So what I'll do is I'll take my moles that I have and divide it by my total number of liters. The problem is in the question they didn't tell me how much NaOH was added. They just told me the concentration of the NaOH. But I know that at the equivalence point, the moles of the acid and the moles of the base are equal to one another. So let's write this cool equation. Since the moles of acid are equal to the moles of base, and I know that moles are equal to molarity times liters, what I could say is that my molarity of my acid times my volume of my acid is equal to the molarity of my base times the volume of my base. Hey, see how I just substituted molarity times liters, or molarity times volume, for the moles of acid and for the moles of base. Now I know that my molarity of my acid is 0.025. And I know that the volume of acid that I used was 40 milliliters. And I can keep it in milliliters in this equation because the volumes are eventually going to cancel out when I divide both sides by it. Now, I know that the molarity of my base is 0.05 molar. And I know that the volume of my base is totally unknown. And that is what I want to find out. So divide both sides by 0.05 molar, 0.05 molar. These guys cancel out. Go ahead and run this through your calculator, and it turns out that the volume of the base is 20 milliliters. So it turns out that I added 20 milliliters of this NaOH. So when I'm done adding 20 milliliters of the base to 40 milliliters of the benzoic acid, my total volume of solution is then 40 plus 20, or 40 plus 20, 60 milliliters total. Now I can take my moles that I have, going back to the ice table, 0.001, and divide it by my 60 milliliters, or 0.06 liters, because remember, moles divided by liters gives me my molarity. And if I take 0.001 divided by 0.06, I have a starting molarity of 0.01667. 0.01667. And of course, if I write this into the ice table, this is my initial value, and I will lose x here. I will gain x over here and gain x over here. And so this is my ending value, actually, 0.01667 minus x, x amount here, x amount here. I can now write that into a equilibrium constant expression. I'm just going to slide the table down here just a little bit, where it ends up being x squared, those are my products, divided by my 0.01667 minus x is equal to the K sub B of the benzoate ion, because notice it's the benzoate ion right here that's acting as a base. It's taking a proton away from water. Well, like I said before, I can't look up the Kb of benzoate ion, but I do know the Ka. I looked up the Ka, and I know that the Ka times the Kb is equal to 1 times 10 to the negative 14th. And if I look back up to the top of the page here, the Ka of it was 6.3 times 10 to the negative 5th. This times the Kb is equal to 1 times 10 to the negative 14th. This says K sub B. And that's the thing that I'm going to solve for, is the KB. So if I divide both sides of the equation by 6.3 times 10 to the negative fifth, 6.3 times 10 to the negative fifth, whoops, negative fifth, sorry, those will cancel. Then I can punch that into my calculator and I get a KB equal to 1.59 times 10 to the negative 10th. So this is my KB of the benzoate ion. I can ignore this X and say that it's small. Multiply both sides of the equation by 0.01667. That makes this cancel. And then of course take the square root of both sides. And when I do that, I get X equaling 1.62 times 10 to the negative sixth. Now what is X again? Look back up to your equation if you forgot. X is the OH minus ion concentration. Hey, that's going to help me find the pH, right? Take the negative logarithm of this. Take the negative log of this, and I get approximately 5.78 for a pOH. Subtract that from 14, and I end up with a pH of 8.21. Fun problem, huh? Lots of things to do in that. Remember, at the equivalence point, we have equal moles of acid and base. We use the molarity triangle once again to find the number of moles. We use that then divided by our total number of liters that we had to calculate using MA times VA is equal to MB times VB. We ice tabled it, and then what we did was we solved for the OH minus ion concentration, which we called X here. Took the negative log of that to find the pH. Last problem is a similar weak acid-base titration problem, but in this case we have 40 milliliters of 0.1 molar NH3, and it's titrated with 0.1 molar HCl. So in this case, when we write the balanced chemical equation, NH3 plus HCl, we have a weak base and a strong acid. And the weak base is going to acquire a proton, and the strong acid will just give up its hydrogen quite readily and form Cl-, which will spectate, of course, and do nothing. At the equivalence point, there'll be none of either of these left, but we will have a significant amount of NH4 plus that's formed. NH4 plus is known as the conjugate acid of NH3, and therefore the solution will act slightly acidic. Writing the equation is the key. Understanding that the conjugate acid is going to act acidic and therefore being able to react with water is the key to doing these problems. Look at what your ions are, look at what the strongs and the weaks are, and then take the weak thing and write an equation with it. So at equilibrium we'll have NH4 plus reacting with a little bit of water and acting weakly acidic to form some H3O plus and some NH3. We can now write an ice table, initial, change, equilibrium, and we can figure out how much NH4 plus we have and therefore solve for the H3O plus ion concentration. We're told that we have 40 milliliters, 0.04 liters of 0.1 molar NH3. So if we multiply those together, we end up with 0.004 moles of NH3 to start with. We need to divide this by our total number of liters to get the concentration of NH4 that we have at equilibrium. Our total number of liters is unknown until we figure out how much HCl was actually reacted. To do this, we can use the relationship at the equivalence point. At the equivalence point, we know we have equal number of moles of acid and base. And since we know there's equal number of moles, using the molarity triangle, we can say that molarity of the acid times the volume of the acid is equal to the molarity of base times the volume of the base. The molarity of the acid, once again, is 0.1 molar. The volume of the acid is unknown. The molarity of the base is 0.1 molar. The volume of the base is 40 milliliters. You can see that when I divide both sides by 0.1, the 0.1s will cancel and my volume of acid is 40 milliliters. So 40 for the acid, 40 milliliters for the base, 40 for 40 is 80. So when I find out the concentration, I'll divide up 0.004 divided by 0.08 because it's 80 milliliters. And so my concentration of NH4 at the equivalence point is 0.05 molar. 0.05 molar. None of this and none of this at the start. My change, I'll lose X, gain X, gain X. So I'll end up with 0.05 minus X, X amount, and X amount right here. So I can write the equilibrium constant expression now, where x squared divided by 0.05 is equal to my Ka of NH4 plus. Now I might not know the Ka of NH4 plus, but I certainly can look up the Kb of NH3 in the back of the book, and I know that Ka times Kb is equal to 1 times 10 to the negative 14th, and so if I know one, I can find the other. The Kb for ammonia is 1.8 times 10 to the negative 5th. This is equal to 1 times 10 to the negative 14th times the Ka. Dividing both sides by 1.8 times 10 to the negative 5th will solve for my Ka. And that turns out to be 5.56 times 10 to the negative 10th. 5.56 times 10 to the negative 10th. So solving now for x, I can multiply both sides by 0.05, and then I'll take the square root of that, and I end up with an x equaling 5.27 times 10 to the negative 6th. That's my x, and if I forgot what x is, I can take a look back up here in my equation and notice x is my H3O plus ion concentration. If I take the negative log of this answer, I end up with 5.3 as my pH. These two examples illustrate how you can find the pH at the equivalence point when you have a weak acid titrated with a strong base and a weak base titrated with a strong acid. Keep the steps in mind. The most important step, once again, is figuring out what is causing the pH to change at equilibrium, and it will be either the conjugate acid or the conjugate base of the weak, in this case, base or acid, and then taking that weak acid or base and reacting with water and writing an ice table, then using relationships like Ka times Kb equals 1 times 10 to the negative 14th to find the Ka or Kb or whatever is needed, and then writing it into the general normal equilibrium expression and solving for x, taking the negative log as necessary to find the pH or the pOH.